Calculus, welcome back. This is going to be our second video that's going to discuss differential equations. And I have a differential equation written up here. And I want you to just look at it for a minute and compare it to the one that I talked about in the last video. And just maybe think about what is the main difference that you see between that one and this one. There's a huge difference, actually. It is a differential equation because it has a derivative in it, and it's an equation. But here's the big difference. Here, dy by dx is not just a function of x. Okay, notice dy by dx is x squared divided by y. So this says that the value of the derivative of y depends not only on the value of x, but also on the value of y. Now, the general solution to a differential equation like this is going to be the same, going to have the same structure as the solution to the differential equation that I talked about in the last one. It's going to be a family of functions, all of which satisfy this differential equation. So it'll be a family of functions for which all of which would have this as their derivatives. Okay, but it's the way we're going to arrive at that solution that's going to have to be a little bit different. This is called a separable differential equation. The reason this is called a separable differential equation is because I can use just some simple algebra here to completely separate the two variables, say all the y's on the left side and all the x's on the right side. Okay, it's very easy to do, and it's the first step. Okay, it's the first step. On the AP exam, this is the only type of differential equation you'll see other than just the elementary type that I talked about in the last video. But this is the only type you see. So if you see a differential equation where there are both x's and y's somewhere on the right side, you know that you're going to have to separate the variables as your very first step. Okay, I'll make that clear. I know the AP exam is going to be a little bit different this year. But in every past AP exam, when there's been a separable differential equation, it's usually 5 or 6 points just for solving this. And if you don't separate the variables in the first step, you're going to get 0. There's no way around it. So remember this: if you get a differential equation with both x's and y's on the right side on the AP exam, you must separate the variables first as your first step. So that's what I'm going to do here. And so what I'm going to do is I'm just going to get everything with a y in it on the left side and everything with an x in it on the right side. So I'm just going to multiply the y over to here. I'm going to multiply both sides of the equation by y and get y times dy equals, and then I'll multiply the dx over to the right-hand side. I'm multiplying both sides of the equation by dx. So I get x squared dx. Okay, that's the first step. The variables are now separated. There's nothing but y's on the left. There's nothing but x's on the right. Okay. Now, from here, what we're going to do is going to look pretty familiar. We did the same thing in the last video. But what I'm going to do now is I'm going to integrate both sides. This side, if you notice, I'm integrating with respect to y because there's a dy there. On this side, I'm integrating with respect to x because there's a dx there. So I'll find the antiderivative of y, which would be y squared over 2 plus c. But I don't actually have to write a plus c on the left-hand side. Because if you think about it, I'm going to have to write a plus c on the right-hand side anyway. And if I subtract this c from both sides, I just get another constant over there. The constant that I'd add here can have any value. The constant that I'd add to the right side can have any value. So their difference can also have any value at all. Okay, so I'm not going to put a plus c on the left when I do the anti-differentiation. I am, though, of course, on the right, and that c right there is going to, absorb the c from the other side, okay? So long story short, you don't have to add a plus c on the left side, you do on the right side. Okay, now remember the solution to a differential equation is going to have to be a family of functions, all of which satisfy that original differential equation. So I have to solve this for y. To get a family of functions, I have to solve this for y. Well, okay, looks like I can multiply both sides by 2 to get y squared equals x cubed over 3 plus c times 2. I'll just write the times 2 out there for now. And yes, I do know that I can multiply them, I can distribute the 2 through. And then the next thing I'm going to do is I'm going to take the square root of both sides. Now remember, if I take the square root of both sides, I'm going to get a plus and a minus on the right side. So I'm going to get y equals plus or minus the square root. And I will go ahead and distribute the 2 here. I get 2x cubed over 3 plus 2c. And, you know, I can write that as plus 2c, but, you know, if you think about this for a second, 2 times c is really the same thing as c here, since c could be any number at all. This isn't wrong or anything, but probably most people may just leave off that 2 there. So this is my family of functions, okay? Notice I can have either a plus or a minus here, and this is the result. Now, that is the general solution to that original differential equation. I'd like to now do a particular solution, okay? So I'm going to erase quite a bit of this, but not all of it. Let's say you were asked to find the particular solution for this differential equation for the case where f of 0 equals 4. Okay. Well, you know, that means that the solution curve, okay, the particular solution is going to have to pass through the point 0, 4, because when x is 0, the value of the function that is the solution to this differential equation has to be 4. The first 2 steps are going to be exactly the same. That's why I did not erase them. Okay, so I separate the variables. I guess that is actually 3 steps. I separated the variables, I integrated both sides, and this is what I got. Okay, now listen. This is the place where I'm going to make use of the initial conditions to find the particular solution. Okay, so it's right here that I'm going to substitute 0 in for x and 4 in for y. So I get 4 squared over 2 equals 0 cubed over 3 plus c, which gives me c equals, that's 0, so that's just going to be 16 over 2, so it looks like c is 8. Okay. So I solve for c right after I do the anti-differentiation. Now that I know that c has to be 8, I can write y squared over 2 equals x cubed over 3 plus 8. All right, now I am going to carry this out because there's something we have to, of which we have to be aware here. I'm going to solve this for y. Okay, so I'm going to get, Teddy, make sure can you see this okay? Down there?
Yeah.
Okay. So I'm going to write y squared equals let's do this, 2x cubed over 3 plus 16. Okay, I multiplied both sides by 2 to get rid of that division by 2. And now I have to take the square root of both sides. If you don't mind, I'm going to erase maybe a little of this at the top so I have some space to do it because this is important here. So again, y equals plus or minus the square root of 2x cubed over 3 plus 16. Now, this is not one function. This is 2 functions. This is y equals positive radical that, and it's also y equals negative radical that. So I don't have my solution curve yet. Okay, I don't have my particular solution yet. I'm going to have to make use of the initial conditions one more time. Okay, so this says that f of 0 equals 4. Well, one of these two cases, either the positive radical or the negative radical, should make this true. So let's test it out. 4 equals plus or minus the square root of 2 times, now x is still 0, okay, so I get 0 plus 16. So, which one of these do I need to be completely correct? Well, 4 is obviously equal to positive radical 16. So, to get my final solution, I don't have to have this plus or minus. I can't have the plus or minus, it's not a single function. So, since I use my initial conditions, and it turns out that in order for this particular solution to pass through the point 0, 4, I need not the plus or minus, not the minus, but just the positive radical there. So I erased both the plus and the minus, and now it's just y equals that. So this is my particular solution to the original differential equation for the case where f of 0 equals 4. All right, Teddy, how are we doing time-wise, boy?
11 minutes, 30 seconds.
I'd like to do one more. And there's a reason why I want to do this one. Y by dx equals, I think this marker might be wearing out a little bit. I'm going to switch to blue. In fact, let's make this even simpler, because there's something actually I want to use. Okay. Take a look at this. Okay. dy by dx equals 3 times y. K is 3. Is everything going okay over there? Sorry for the interruption. I think Thomas was feeling a little bit ill there.
Sorry about that.
dy by dx equals a constant times y. Okay. Just think about that for a second. This says the rate of change of y with respect to x is directly proportional to the value of y right now. The rate of change of y is proportional to 1. The rate of change of the amount of money that you have is proportional to the amount of money that you have right now. Okay, you may recognize this as kind of a compound interest situation, or the rate of growth of a population is proportional to how many people are alive right now. Okay, the more people that are alive right now, the faster the rate of growth, the more money you have in your bank account, the faster it grows for any particular interest rate. We're going to solve this. Okay. I'm going to separate the variables. dy over y equals 3 dx. Okay. I divided both sides by y and multiplied by both sides by dx there. Now I'm going to integrate both sides. Now we all remember that the antiderivative of 1 over y is the natural log of y. And remember, I don't have to put the plus c there, I'm going to put it on the other side. The antiderivative of 3 is 3x, and that's where I get the plus c. Now, I'm going to have to solve this from y to get my general solution here. The first thing I need to do is to undo the natural logarithm. Okay, so to undo a natural logarithm, remember the inverse of taking the natural logarithm of something is to exponentiate to base e. So I'm going to exponentiate that side to base e, which means I also have to exponentiate the entirety of the right side to base e. Okay. Now the exponentiation to base e and then log base e cancel each other out. So I have the absolute value of y equals, and over here, I'm going to do just a little, I'm going to use the laws of exponents to change this into e to the, and remember if I have, if I'm adding exponents, that's going to be the same as e to the 3x times e to the c. Okay, if you don't see how I got that, think about going from here to here. If I'm multiplying two expressions with the same base, I add the exponents. So e to the 3x times e to the c is e to the 3x plus c. Now, e to the c, that's just a constant. Okay, because remember, c can be anything at all, so e to the c can also be anything at all. So I'm going to rewrite this as just absolute value y equals, I'm going to change this to just a constant, I'm going to call it k, okay, times e to the 3x. Now I still don't have y by itself because it has absolute value brackets around it. And now the way to undo absolute value brackets is to simply, remember this says the absolute value of y has to equal this. Well, that's true if y is equal to this, or if y is equal to the opposite of the k times e to the 3x. So essentially what I do is I rewrite this, I lose the absolute value brackets, and I have to put a plus or minus k times e to the 3x over there. And then of course k can be anything at all, so I really don't need that plus or minus there necessarily the way it's written here. I mean, it's not wrong if I leave it there, but this is the family of functions that are solutions to that original differential equation. If you look at this, think about where you've seen an equation in this structure before. Y equals a constant times e to a constant times x. And think about the continuously compounded interest equation. P equals P naught times e to the RT. It's the same thing, okay? Continuously compounded interest. If your money grows at a rate, if your money grows at a given interest rate, compounded continuously, this is the equation that describes how it grows. You've got your initial amount here, e to the, there's your interest rate or growth rate, and there's your t is your time. And it's a solution, that's a solution to the differential equation, dy by dx equals a constant times y. Okay, now if I were trying to find a particular solution for this, it would be at this stage right here. As soon as I do the anti-differentiation, remember that I would use the initial conditions to substitute in for x and y and solve for c. From there, I substitute whatever value c is back into here and proceed to solve for y the same way I did before. Okay, Teddy, how are we doing time-wise here?
18 minutes.
Okay. Listen, you could probably do 6-5 now, and maybe try doing that linked AP exam. And Grant, I know you're not taking the AP exam, but I mean, if you want to do it, it's good practice. And please email me with any questions. I know you can find the answer key rubric online, but if you can't figure out what it means, the answer key, the solution key or whatever, please email me. We can work through it together. Thanks for watching. Have a great day.